In this video, we're continuing our discussion of forced vibration of single degree of freedom systems, and here we're considering non-harmonic periodic forcing functions. So far, we have only examined harmonic forcing functions or sinusoidal forcing functions, but there are many other non-harmonic but periodic forcing functions that can exist. Periodic forcing functions need only to repeat themselves at a regular frequency to be periodic. They don't need to necessarily be a sinusoidal function. So we want to be able to figure out the response of these non-harmonic functions. So for example, we have considered harmonic functions like the first one shown here. But these are other examples of non-harmonic periodic forcing functions. So we can have something like a square wave that repeats after some interval of time. We can have kind of a sawtooth wave. We can have some sort of other type of a function that repeats. The key here is that that there is this periodicity to it. So where after some period of time, the function repeats. So in considering these types of functions, to do the analysis, we need to use something called Fourier Analysis. So in general, whenever we have a periodic function with a period, tau is equal to 2 pi over omega, where omega is the frequency, it can be expressed as a Fourier series, which is a sum of harmonic functions. So for example, any periodic function, f of t, can be represented by this sum, where we've got something like an a0 over 2, and then the sum of aj cosine j omega t, and a sum of bj sine omega t, or sine j omega t. Where a is given as the integral from 0 to tau of f of t dt times 2 over tau, which is essentially equal to 2 times the average force, the average F. The aj's are equal to this expression here, so the 2 over tau times the integral of 0 to tau ft cosine j omega t, where j goes from 0 to infinity. And the bj's are given as this expression here, and again, j goes from 0 to infinity. So we have this infinite series, which is known as the Fourier series. So if we think back to the equation of motion for a damped spring mass system undergoing forced vibrations, we had this expression, mx double dot plus cx dot plus kx is equal to f of t, where f of t in the previous examples was this harmonic function, but now it can be really any function, any periodic function that we're considering. Now when we substitute the Fourier series for f of t, we get this expression. So this, again, we're using this Fourier series to represent f of t. Now we want to find the steady state solution to this equation of motion, and we can do that by using the principle of superposition. So essentially we want to add up the individual components for the solution. So the solution to this equation is the sum of the different components. So the sum of this equation plus the sum of this equation plus this equation. Now the steady state solution for the first one, this is, you can see, does not vary in time. It's just a static load a0 over 2. So the steady state solution for that is simply a0 over 2k. So f0 over k. Now we've already shown that the solution for this equation, mx double dot plus cx dot plus kx is equal to f0 sine omega t, is given by these values here. So the response is this f0 over k divided by this square root term times sine omega t minus phi, where phi is given as this angle here. So using the same method, we could show that the solution to this equation, where now we've got f0 cosine omega t, is equal to this here. And so basically the only difference is that we have cosine omega t minus phi. So the steady state solutions to these are, to the two equations shown in 6.4b and c are shown as here. So this was the one for the A's, and then this is the one for the b's. So this is basically taking the previous results and applying them to our new equations. So you see we've got an AJ, J's, cosine j omega t minus phi j, and then similar here, bj, we've got some j's, sine j omega t minus phi j. And the phase angles are given as shown here. So now here's some important notes. We could see that the amplitudes and the frequencies for the jth frequency depend on j, so they're not constant. The terms with the frequency component j omega closest to the natural frequency will have the largest dynamic magnification factor. And as j continues to increase, the amplitude of the jth terms decrease because of the decreased contribution in the dynamic magnification factor. So a reasonably accurate solution can be obtained using only the first few terms. Now it's also important to note that if the periodic forcing function is too complex or is determined experimentally, then the integrations in our previous expression, 6.2b and c, may not be available analytically and will have to be approximated numerically. To do this, we can consider the period tau to be broken into n, which we'll consider as an even number, of equally spaced time intervals delta t, so that tau is equal to n delta t. So tau is the whole period, and we're breaking it into n intervals of delta t each. Now if f1, f2, up to fn represent f of t, our function, at the different values of time, then the Fourier coefficient can be approximated as with these expressions here. So instead of using an integral, we can use this finite sum from 1 to n. And again, we have j's here, where j goes from 1 to infinity. Now, once the coefficients are known, then we can proceed with the solution by replacing omega with 2 pi over tau. So these solutions only represent the steady state solution, which is typically what is of interest. But if we do want to look at the transient solution as well, then we have to solve for the homogeneous equation mx double dot plus cx dot plus kx equals 0, which adds this term to the solution, or x naught, or x of t, is equal to e to the minus zeta pt times this, where p again is the natural frequency. And these a and b must be found using the complete solution. So we have to find the particular part first, and then we can go and find the a and b based on the initial conditions if we want to. This is really only necessary if we want to look at both the look at the transient solution.